for the Center for Geotechnical Modeling in the Department of Civil and Environmental Engineering at UC Davis. I think that's a fancy way of saying they do earthquake stuff. And so his presentation is going to be talking about the Center for Geotechnical Modeling and results and impacts from an NSF Network for Earthquake Engineering Simulation program. So thank you very much.
I'd say I'm a little intimidated about going after this morning's session and all the problems we've had and coming up and talking about earthquakes. See if we can make it through the session. Apparently I'm the token earthquake engineer that came to the Shake It Up conference. Doug Hartline invited me to come down. I worked with Doug about 15 years ago when we started this NEES simulation program. Our facility is remote from campus, and we were working on internet at that time to collect data, and we drive to campus, put it on our servers to share with people. Doug helped us get onto the high-speed research network, and now we have, shortly after that, we went from Ethernet being some of the highest bandwidth available on campus, straight to the campus edge router. So what I'm going to do today is I'm going to try to go very quickly. If somebody wanted to bring me a cup of water so I can make it through fast, that'd be great. I'm going to talk about NEES, the National Network for Earthquake Engineering Simulation, and talk about how we developed this network as a shared collaboratory to address national needs for infrastructure. I'm going to bring it down to the local level and talk about the UC Davis facility, how it works, what we do there, the kind of things that we've done with sharing data and impacting civil engineering, trying to make a difference in how we design our society. And then bring it back up to the national level again on sharing data and cyber infrastructure available for that and how people are interacting and where are we going in the next stage of cyber infrastructure. So obviously seismic risk, earthquake safety is an issue that spans across the entire country. In California, it's a particular risk. FEMA has estimated something like $5 billion annualized cost of earthquakes in California. If we talk beyond just the obvious avoidance of loss of life, right? We obviously don't want to have anybody lose their life during an earthquake, but there are major costs that go beyond that in developing a resilient society so that when the earthquake strikes, we can recover quickly. So we recover quickly by, one, avoiding damage to begin with, and two, by trying to control that damage so that we recover quickly afterwards. We can't necessarily avoid all damage. Earthquakes are very powerful forces of nature, so hopefully what we can do is try to avoid that and recover from it quickly afterwards. So in the beginning, NEES began as the National Science Foundation George E. Brown Jr. Network for Earthquake Engineering Simulation. Began in 2000 as an initiative to build research infrastructure in the country, to create physical facilities to do advanced experimental work, with the idea being that we needed to collect some data. Thank you. We needed to collect some data because our computational tools at that time were ahead of our physical modeling tools. We're doing these really fancy numerical models that tell us things that happen, but how do we know? What's the proof test? What's the reality check of those numerical models to say that they're accurate? So what we wanted to do was build a national scale facilities, shared use facilities that we could use to validate these numerical models, and we could move beyond and increase our resiliency. So it's a geographically distributed, ooh, that's a terrible color, but at least it's working. It's a geographically distributed set of facilities. There's 14 equipment sites across the country. There's several in the UC system. There are 5 or 6 of us in California. And they're all tied together with, we're all unique facilities, experimental facilities, but we're all tied together with common sets of access, common sets of data, common sets of a cyber infrastructure, so that anybody in the country can go to these facilities and do experiments. Anybody from the country can go and download the data that's collected at these facilities and run it for their own analyses. This was, the last 5 years has been about a $100 million project to support these facilities. As I mentioned, they're big, they're unique facilities. There's 6 structural facilities of the 14. NEES from the very beginning was a real culture shift in the way that earthquake engineering research was done in this country. It's the first time that the National Science Foundation was funding these centers directly. So if you ran the shaking table facility in San Diego in the upper right, or the shaking table facility at Buffalo in the middle, you got so much money from the National Science Foundation to run your facility and to be open and operating. And then other people could write proposals to the National Science Foundation to come and do experiments at your facility. So when you had some unique structural testing lab, like the University of Minnesota lab in the middle left there, it's not just University of Minnesota professors doing research at that lab now. It's anybody in the country could write a proposal and come and do that work. So that idea of shared facilities was a totally new concept, and interdisciplinary collaboration changed the culture immediately overnight. The non-structural testing facilities. They're shown in this picture. I didn't want to try to go through things fast. The other real key aspect of this is anybody using the facilities, you had to use a common data format. You had to use common data structures so that anybody else could then download and use your data. Right? There's unique data being collected, unique experiments being performed. We want to get as much knowledge from that as possible. We want people to learn from these experiments and for this to become and improve society's ability to react to earthquakes. And so it's really a cultural shift to have this cyber infrastructure and shared data, so you're not just doing an experiment for yourself, you're doing an experiment so that everybody can benefit. UC Davis, hopefully that's not my time over already. The UC Davis Center for Geotechnical Modeling, we operate a 9-meter radius geotechnical centrifuge. It's much brighter than that in real life. It's the largest centrifuge in the world. It's a very unique facility. It's outfitted with a shaking table. You can see some of the complex experiments we're doing on this machine. The machine itself is something like 150,000 pounds. You can imagine when we're running, it's running at about 200 miles an hour. And while this thing is moving around, we're generating earthquakes. So why are we doing this? Well, the whole idea is, we want to basically generate case histories where we can see how structures behave during earthquakes. This could happen, is very relevant in cases where we might have new kind of proposed structures. So wind turbines, offshore wind turbines is a pretty new growth arena. We want to build these things in areas where they might have some seismic risk. You might have some earthquakes. And how are they going to behave? We don't want to build them and then see how they behave during the earthquake. We want to be able to do some experiments and see how they behave. Same thing for offshore oil platforms. This is the subsea manifold for offshore oil distribution. The exploration of oil is moving into areas where there's more seismicity. We don't want to discover that our offshore oil structures don't do well in seismic events. After the seismic event, we want to do the analysis beforehand. So the centrifuge is a useful tool in doing anything that's gravity related. Scale model testing where the problems that are being studied are affected by gravity. That could include things like frost heave. Earthquakes and explosives are big ones that centrifuges are used for, but there's a lot of other things like wave loading, sea ice flow, many problems. I'll give you an example of one problem that spanned through many years of study at UC Davis, and that's soil pile interaction, soil foundation interaction, especially during earthquakes and liquefaction. So this is an example. This is an example of a fairly modern bridge that failed in a fairly recent earthquake, 1995 Kobe earthquake. And what happened during this earthquake, you can imagine, first of all, that bridge deck used to go straight across. During the earthquake, the soils beneath this bridge abutment liquefied. And so the soils that you can see on the surface spread into the water. So this lateral spreading pushed on this bridge bent and basically pushed this part of the structure over to the point where this bridge deck fell off of its seat. So that lateral spreading due to liquefaction is a real problem thing. Obviously, it was not adequately captured in the design of this bridge. That's a problem that we struggle with in civil engineering design. So what my centrifuge experiment looked like, this is an experiment we did shortly after that, trying to capture, what we do in a centrifuge experiment is we build a scale model of a similar structure where we try to capture the same physics. And then we try to understand the problem so that we can take that and build it into engineering knowledge. So this is an example where we have a structure. This is a lot like what that bridge bent looked like. We have a structure, and it sits on piles, and we have soil that liquefies, and we have this other soil that doesn't liquefy on the top. During the experiment, there's an open channel down here. The soil liquefies, and the upper soil spreads and pushes on the piles, similar to what we saw in Kobe. doesn't look very real. A lot of people look at that and say, yeah, we're gonna do that, but why do I think that's what really happens? So I'll back up and I'll say, your common sense, everybody is actually more comfortable with scale model testing than perhaps they think they are. Nobody assumes that they built the space shuttle and stuck it on the back of a 747 and then tested it to see what would happen, right? They built the scale model, put it in a wind tunnel, and then they trusted that wind tunnel results to actually put it out into the field. So they did scale model testing. They ran through the laws of physics, and they assumed that they actually had some knowledge of what was going to happen. Same thing with offshore platforms. We're not going to build an offshore platform and then see if it survives a hurricane. We're going to build a scale model. We're going to put it in a wave tank. We're going to simulate the wave loads, the big wave tank, and how things work. We're going to capture those physics, and we're going to try to build a safe structure. We do the same thing with geotechnical engineering, scaled structures. All right, but these aren't on a centrifuge. Why do we put things on a centrifuge? That seems crazy. It's complicated. It's a big machine. So how does the centrifuge work? Well, the centrifuge is this 9-meter radius machine. Like I showed you, there's a whole bunch of computers on board. There's a whole bunch of, there's a shaking table out here on the end of the platform. There's massive servo controllers. We have fiber optic gigabit Ethernet directly onto the centrifuge. Anything that's connected here, any network device that's on that bucket there is actually connected straight to the campus edge router over gigabit Ethernet. As the centrifuge spins up, that bucket spins out. And so the G-force is always basically down on the model. So at 75 Gs, you can see the bucket is swung completely out. And the centrifugal weight is simulating the centrifugal force is simulating the weight of a larger structure. So if you have a 2-foot deep soil, that centrifugal load becomes 150 feet. At 75 Gs, it's going about 90 RPM. That's 200 miles an hour. Remember, that bucket weighs 20,000 pounds. As we're spinning around, that big shake table simulates the earthquake. Okay, so and that shake table is something like a 25,000 horsepower shaker. Very violent machine. Imagine going around 200 miles an hour and then shaking. That's crazy. Why would us to even do these experiments? But it's pretty cool. So why do we do this? When we're doing a scale model test on the centrifuge with this big model container, our container is about 1.7 meters long. At 75 Gs, that's representing something that's like 130 meters long. Okay, so that's much larger than even the orders of magnitude larger than the largest shake tables that are in the world. So we can look at large areas. And the reason we do that is because it's really critical in soils to get the stresses correct. So if we're going to do a reduced scale model, we have to get the stresses inside the soil correct, or else it's just not going to behave the same. Don't get the physics right. This is an example of one of the projects we've done under NEES. This is something that happened because of NEES and this national network. We could build up and do these complicated experiments. This is an entire city block that we tested. Okay, so you can see, when we do an analysis of a structure, and if you're in any engineering, you see this all the time, you analyze the building that you're building. You analyze what's the effect of the earthquake on your building. You don't ever think about the fact that, wait, there's a great big building next door to me. What's the effect of the earthquake on that building and that building's effect on my building? And so it's a new concept that we were studying at Davis with this city block project, something that's really important in urban areas. The centrifuge itself is outfitted. This is still the same city block project. It's a different set of models. These are smaller models, but there's a whole bunch of structures there. There's something like 250 sensors that we mounted in one of these models. It's a big part of our NEES upgrade was putting in all this high-tech electronics. And we just replaced the system. I think I spent $100,000 on data acquisition last year replacing this data acquisition system. It's all high speed. We have high definition cameras. We have high speed cameras. A lot of different things to try to characterize and capture what's going on during the experiment. You can see what happens actually during the earthquake. This is that city block project. You can see the structures sitting next to each other and all the different instrumentation. The earthquake itself happens very rapidly. The time is scaled. So a normal earthquake might be 30 seconds long of shaking. At 60 Gs, that earthquake is only half of a second long. So as we're spinning around 200 miles an hour, we're dealing with this earthquake. It's like shooting a shotgun. It's just extremely violent action. So what's that done? This is kind of the best example of what NEES has done. That experiment, what was that project team? How did that actually work out? That project team, you can see the control room during that experiment. There's 3 different PIs from 3 different universities, Berkeley, San Diego, UC Davis. There was another PI at SUNY Buffalo that was working on this project. We had 6 graduate students and a couple of undergraduates. We had 8 different students in the control room working on the experiment at one time, plus our staff. So there's a lot of people working on that experiment. They're all collecting that data simultaneously. Then what they're all going to do is they're going to take that data, they're going to store it centrally in the NEES repository, and all of them are going to go back to their home universities. They're all going to work on the data simultaneously, collaboratively, but they're all going to be doing their unique things with the data. And it's a real model for not just this team, right? This team needs to be able to collaborate and share the data. And then once those tools are in place and once those structures are in place so that the team can collaborate, then you can think about how do people access it that weren't part of the original team. They're going to access it in the same ways. They're going to want to know the same kind of. All of that information needs to be stored in a repository so that the future people can. Going back to the idea of doing these advanced instrumentation, the advanced experiments, a big part of NEES was building up the infrastructure so that we could do experiments that couldn't be done before. So this is an example of an experiment. This is just a model that had loose sand. On the left, so you have loose sand during the earthquake, you generate pore water pressure. On the left, it was outfitted with these drains that were supposed to relieve the water pressure so that the soil wouldn't actually liquefy. Yes, they worked. On the right, you have the same soil, but you don't have the drains. And so that water that wants to get out can't get out. So what happens instead is the soil liquefies, and then again, you have lateral spreading. This crust on the top, the lateral spreading. You can see that here in this picture. This offset, originally that was a straight line. After the earthquake, that's an offset. It looks pretty small in the picture. That's a meter of offset in real life. That's certainly enough to fail that bridge that we saw in earlier. I'll point out that this model, you can see all these red dots. These are all pore pressure transducers. You can see them in the model. There's a whole array of them buried along here. This model had something like 60 pore pressure transducers, something that became possible underneath. Every pore pressure transducer is over $1,500. So that's $100,000 worth of sensors in this one model. The experiment just couldn't be done before NEES. The neat things that allows us to do then is do some really neat math on that sensor data. So as an example on the left, remember what we're trying to do is vet out our computational models. We have very advanced computational models. How do we know that they're getting the physics right? How do we understand this? So on the left, what we've done is some really neat math on those pore pressures. And what we've done, I'm not going to explain it, but on the top here, you can see this red line shoots over to the right. That's a direct measurement that the soil was getting loose directly underneath the crust. Okay, so we have a measurement. We say that soil is getting really loose. It's getting really weak. And it's very focused. It's just the soil that's immediately beneath the crust that's happening. So that's the physics. We're measuring the physics that's going on in the test directly. Then on the right, what happens is we run these advanced computational models. And the same thing on this advanced computational model, you can see the blue is kind of what we were originally. And after all the earthquakes and everything happened, you can see that numerical model predicting a very localized loosening of the soil. Okay? It's a very difficult thing to capture numerically, this localization and this kind of loosening. But we can see we've captured it. We thought we could do it in a numerical model. We've captured it in a physical model. We've done some really fancy math to see that it's the same thing. It shows a lot of compatibility, and it's a really robust test of the computational model. That's really going to increase society's ability to design things to be resilient for earthquakes. Of course, a big part of that is not just UC Davis doing this neat stuff and creating numerical models. It's sharing the data, getting it out to where other people are doing their own analysis, right? We want other people to do numerical models, other people to vet their numerical models against it and how well they're doing. So even before NEES, as an example, UC Davis, we created a data sharing policy where we would post all of our data online as soon as we got it. So in the late 90s, we would drive to the campus and stick our data on the server, and you could download it from our FTP site very quickly after the experiments. And people could download the data and use it in their numerical models to try to improve things. We kind of studied that we had kind of a longitudinal study on that in one case. We did a set of 5 experiments on piles, same kind of lateral spreading pile test, liquefaction I was explaining earlier, and kind of watched as people used this data across the world. And over the course of more than 15 years, we saw more than 40 research teams across 15 countries were using this data. They were publishing the data. It wasn't just that they had downloaded it. Right? We didn't care about downloads. What we wanted is people telling us, I downloaded your data, I used it in my numerical models, I used it to calibrate this, I published it in a paper. We had correspondence with people in academia, we had correspondence with people in practice. So it became basically a standard case history to improve liquefaction, soil pile interaction. People doing numerical modeling now, they download this data set to compare to their numerical model, make sure that they're able to get the physics right before they go and do more design. To give you an idea, I mentioned that length of time scale. Just bring that out. That pile project, for example, there was a series of projects over the course of 15 years. Began in the late 90s. The testing, most recently, we see in 2012. It's difficult to measure impact on practice. But one of the real clear measures is, for example, this in 2012, Caltrans issued a new guidance document on foundation loading and deformation due to liquefaction and lateral spreading. This is what Caltrans engineers use. This is what engineers building Caltrans bridges will use to design bridges where they have liquefaction and lateral spreading. And this came out of a lot of the centrifuge tests and other studies that were going on, and the numerical modeling and all the development of the numerical models that go on. And you can see it's more than 10 years going from research to practice, at least 10 years, and that's with rapid data sharing. Back up on the national level, that's a really good example of what we're doing at UC Davis within the NEES network. Obviously, there's 14 equipment sites across the country. Everybody is doing the same kind of things. You could pick any one of the equipment sites and you could pick a similar kind of example, follow it through. The NEES CyberInfrastructure for this data sharing is actually called NEES Hub. It's part of Hub Zero technology at Purdue University. The major cyber-infrastructure components are the project warehouse, the idea of all that shared data being put in one place where people can go and use it. It's also a set of computational simulation tools, the idea of being vetted, open source. Everybody's working with the same computational tools so everybody can develop them and advance them and improve them against the data sets. And then access to high-performance computing. That's kind of the infrastructure that's tying this all together. It's been a challenging 15 years. The idea of building this community and building the collaborative environment around the data. This is an example from just the last 5 years on the use of the warehouse, on the use of the data repository. And you can see actually from 2009 through 2013, or early 2014, there's been a rapid growth in the number of files posted in the warehouse, which is a proxy to how much is the warehouse being used by the people developing the data. Remember, NEES was around for 5 years before this. Honestly, the first 5 years there was a lot of conflict between using something like this centralized repository versus using Dropbox. It's pretty easy for engineers just to throw the files in Dropbox so people can share it right away. Very low learning curve. A centralized repository like this has quite a bit higher learning curve. You have a lot of other features that go on top of it, but getting an engineer to buy into that is a challenging thing. And so 5 years of trying to get people to buy in, and we got 5 years of growth. Just as an example, showing that NEES actually, the idea is it's a United States initiative, but it's been a global, it's had a global impact. It's being used across the world. The red dots is people using that data repository. The yellow dots are people running computational simulations using the open source tools that are available. So there's a lot of international collaboration. There are similar networks in Europe, Asia that are trying to share data between the repositories. So some really interesting, challenging problems. That NEES, as I mentioned, was a 14-year project. It ended in October of 2014. And anybody who's interested in learning more about it, there's this Decade of Earthquake Engineering Research summary book. It's posted on the NEES.org website. You can go and download. You can see a lot of examples of research projects that were done at the various facilities. the discussion about the cyber infrastructure tools, the other things besides the project warehouse, other tools that they had available, and some of the education outreach tools that are available. So, like I mentioned, that ended in October 2014, but obviously we're not done with risk. So what we're doing next, National Science Foundation has a new 5-year solicitation out for NEERI, the Natural Hazards Engineering Research Infrastructure. Don't get married to the acronym. I don't think it's going to last very long. One of the first jobs is for the people who get the award to come up with a new acronym and website, because NEERI.org is already taken. But the idea now is that they're going to tie in not just earthquakes, but going to look at earthquakes and winds, maybe earthquakes, tornadoes, and hurricanes. And you can see the risk across the United States. While earthquakes are focused in the West Coast, hurricanes, tornadoes span across a lot of the East Coast and the Central. So we capture risk across the entire country. And when we're talking about building civil infrastructure, we're talking about building loads and foundations and our civil infrastructure. It needs to be resilient to all these risks, not just one or the other. It's going to be the same kind of construct. There's a headquarters organization. There's cyber infrastructure. You can see in the cyber infrastructure, there's still this NEERI data repository. The NEERI data repository is still an explicit requirement of the cyber infrastructure awardee. Centralized storing and sharing of data it's critical to the mission. It's critical to the National Science Foundation's goals of NEERI. This Computational and Modeling and Simulation Center is an explicit call out that we want to develop community computational simulations. More explicit call for that aspect of the award. And then there's going to be up to 7 equipment sites now. Remember I said there was 14 before. There's up to 7 now, and it's going to include wind. So it's going to be a lot different. $62 million over 5 years. So looking back and kind of thinking about where this has come from, where this is going, like I said, it's a challenging problem. The first 5 years, we look at cyber, I'm going to pull out cyber infrastructure for you. The first 5 years, we had NEES construction. It was a major research equipment facilities construction award. We had 15 independent facility awards, and we had this NEES grid by NCSA. They were developing grid technologies for us to share data in the earthquake engineering community. That was about $11 million of the first $82 million was spent over 3 years. The first round of NEES operations, 2004 to 2009, there was a headquarters organization. There was no headquarters in the first 5 years of construction, just everybody independent. Then all of a sudden we have a headquarters, and we have sub-awards, and we have this NEES IT down at San Diego Supercomputer that was in charge of providing the cyber infrastructure for the environment. So we didn't have grid anymore. Now we had Oracle databases, and we had NEES Central at San Diego. And that was about $4 million a year over 5 years. Then that stopped after 2009, and they had a 5-year competition, and they awarded the next 5 years of operations to Purdue. And with Purdue, they kept the IT in-house. So now there wasn't an IT sub-award. It was NEES Hub, part of that Hub Zero technology that was developed by Purdue. So now they're spending about $2.5 million out of the 20, and they got rid of the Oracle databases, and they went with Hub. Couldn't explain what Hub is. If you want hub.org, you can go to and figure out what Hub is. But that was NEES operations 2014. Now NEERI is going to be 2015, 2019. Like I mentioned, there's 2 awards now: cyber infrastructure plus computational simulation. So it's an explicit call out of computational simulation, and it's something like 5 million of 12 million. So it's grown to be a much higher percentage of the total award. And it's interesting that a big part of this 5-year operation, you can see the headquarters organization now, one of their explicit requirements is to develop the decadal science plan for natural hazards engineering research for 2020 to 2029. So we'll be going through this 5 years, and then part of this 5 years to decide what are we supposed to do in the next 10 years. Always. So just to kind of to wrap things up, I think I went through really fast. Hopefully it made sense. It made sense when I did it slowly. I talked some about the recent past with NEES. We addressed this National Science Foundation. We addressed the national need for earthquake engineering resiliency, advancing facilities, building a cyber infrastructure, and changing the research culture. It's in research now. It's hard to emphasize the amount that it's changed. It's multidisciplinary. It's collaborative. People expect to share facilities. People expect to share data. Nobody is going to do an experiment, collect their data, and go publish a paper now, except for real old school people. Anybody who is graduating, young professors now, just expect to share their data. Center for Geotechnical Modeling. I showed you how the Centrifuge works. It's a pretty cool tool. It's a lot of fun to work there. And the idea is that we're trying to generate knowledge. It's all about generating knowledge. How do we affect people's understanding? Because they're the ones that are going to make the decisions. They've got to stamp the plans. They've got to build things so that we can stand in these great rooms, project over, explain how we learn things. And then talking about sharing data and cyber infrastructure. Sharing data, like I mentioned, it's widely adopted. The impacts are measured over the course of years. We talk about doing things fast. We talked about that some earlier in the presentations. Things are rapid. But when we get down into the actual design and building of structures, actual impact to society, things are measured over years, if not decades. So this is going to be ongoing. It's continuing. We want to make it go faster, but it's going to take people understanding and accepting and changing. But it's the new normal, sharing data. And with that, I just wanted to acknowledge our project sponsors. Hopefully I went through it, and it's lunchtime, I suppose, or on. I doubt there's time for questions, but I'll be around the rest of the day if anybody wants to catch me.